In this lecture, we will start a new chapter, Semiconductor Diodes. Semiconductor Diodes. This is the name of the chapter. And in this chapter, we will learn how a junction is formed between P-type and N-type semiconductor. We will also learn volt-ampere characteristics of the two-terminal device obtained by using PN junction. And the device is called as PN junction diode. So I will write this down. We will learn volt ampere characteristics or VI characteristics of PN junction diode. PN junction diode is a two-terminal device, and there is a difference between PN junction and PN junction diode. We obtain PN junction diode by using the PN junction, and we can do this easily by attaching the metal contacts at the two terminals. So if I attach one metal contact like this, then we have PN junction diode by using the PN junction. We will do the same thing for this terminal also. And because of this, we have three possibilities. First possibility is no bias condition, no bias conditions. In second possibility, we have forward bias condition, and in third possibility, we have reverse bias condition. In this lecture, we will deal with no bias condition, and in the coming presentations, we will complete forward and reverse bias condition of the PN junction diode. Now there is one question. What is the meaning of bias? What do we mean by biasing the two-terminal device? So I will write this down. The meaning of bias. The term bias refers to the application of external voltage across the two terminals. When we apply external voltage across these two terminals, we call it biasing. I will write this down. Application of external voltage across the two terminals is called as bias. And if we apply no external voltage, it is called as no bias condition. So in this lecture, we are not going to apply any external voltage to this PN junction diode, and we will analyze the PN junction diode in this situation. The next thing is the BJT, the bipolar junction transistor. This chapter is very important because we will use the concepts and theories developed in this chapter for learning BJT. BJT stands for bipolar junction transistor, and this is very important topic in analog electronics, and it depends on PN junction diode. So if you have better understanding of PN junction diode, you can easily understand the bipolar junction transistor. BJT is a three-terminal device. This is three-terminal device, and you can consider this as the device having two diodes. BJT you can consider as a device having two diodes in which one diode is biased by the current of other diode. So you can see how much it depends on the concept that we are going to learn. So without wasting any time, we will start with PN junction. We already know what is P-type and N-type semiconductor. In case of P-type semiconductor, we add trivalent impurities. In case of P-type semiconductor, we add trivalent impurities, and because of this, we have holes as the majority charge carriers. On the other hand, for N-type semiconductor, we add pentavalent impurities, and because of this, we have electrons as majority charge carriers. And if we talk about the minority charge carriers, then for P-type, we have electrons as the minority charge carriers, and for N-type, we have holes as minority charge carriers. And if you remember, the minority charge carriers depends only on temperature. because electron gains the thermal energy and breaks the covalent bond. So it only depends on the temperature and it will not depend on the external voltage that we are applying. So this is something we already know, and now we have to see what will happen if we combine p-type and n-type semiconductor together. When we combine p-type and n-type semiconductors together by any means like diffusion or an implantation, these are the process to combine p and n-type semiconductors. We dope one side of the semiconductor with the trivalent impurities and we dope other side of the semiconductor with pentavalent impurities. We will have p-type on one side like this and we will have n-type on the other side. If we consider the p-type, I will clear this portion. If we consider the p-type, then we have positive immobile ions, or we can say acceptor ions. These are the acceptor ions, and we have holes as the majority charge carriers, and on n side we have donor ions, and electrons are the majority charge carriers. So this is what we have when we join p-type semiconductor and n-type semiconductor, and this is the junction, and if we talk about holes, then concentration of hole is higher on the p side as compared to the n side, and because of this we have concentration gradients of holes from p side to n side, and similarly we have concentration gradient of electrons from n side to p side. And if we try to understand this thing by the help of pressure difference, let's say we have A and B, these are the two regions, and pressure at A is PA and pressure at B is PB, and let's say PA is greater than PB, then air will flow from A to B, right? The same thing will happen with holes. On P side, concentration of hole is higher, so holes will move towards the N side like this. And if you talk about electrons, then concentration of electron is more on N side, so electrons will move to P side like this. And as you can see, we have movement of charge through the cross-sectional area. If we consider this junction, and let's say the area of junction is A, then there is movement of charge carriers through this area, and whenever this happens, there is current. And as this process, the process of movement of charge carriers from high concentration to low is called as diffusion, we call this current diffusion current. This process is called as diffusion, and the current is called as diffusion current. This diffusion current is very important, and we have to use it a lot while solving the numerical problems. And diffusion current is because of majority charge carriers. So we have one new thing with us, diffusion current. So let us try to understand it once more. Diffusion current is because of the movement of charge carriers, the majority charge carriers, from high concentration to low concentration. We call it diffusion current because the process of movement is called as diffusion, and this is because of majority charge carriers, right? The next important thing is depletion layer. Now we have to understand how depletion layer is formed in PN junction diode. Because of diffusion, holes from P side combines with electron on N side, because we have electrons as the majority charge carriers on N side, and in the same way electrons from N side combine with the holes on P side, and as the recombination takes place, immobile ions will surface out. I will write this point down. Immobile ions will surface out because of what? Because of diffusion. Now what do we mean by immobile ions will surface out? What do we mean by surface out? Surface out is nothing but uncovering of immobile ions. This acceptor ions and this donor ions are immobile ions because they are fixed, they are not moving, and when we uncover them, we call immobile ions are surfaced out, because initially electrical neutrality was maintained. With acceptor ions we had holes, so electrical neutrality was maintained. In the same way, with donor ions we had electrons. But as these holes are combining with electrons, we are left with positive and negative ions. Because of this, depletion layer is formed in PN junction diode. The region with no mobile charges but only uncovered immobile ions is called as depletion region. I will write this down because this is important. Depletion region. In this region there is no mobile charges, but only uncovered immobile ions are there. And as I have already explained why there is no mobile charges, because the holes and electrons are combining with each other and we are left with negative and positive ions. So I will try to draw this quickly. I will try to draw the depletion layer quickly. These things are very important because this will help you understand the basics, and after this you can understand any concepts in analog electronics. And if you fail to understand these important points, then it will be very tough for you to understand the coming presentations. First I will make P side. We have acceptor ions on the P side, and on the N side we have donor ions, so we have positive sign for them. Holes are the majority charge carriers in P side, so we have holes as the majority charge carriers, and we have electrons as the minority charge carriers. In the same way, for N side we have electrons as the majority charge carriers, and we have holes as the minority charge carriers. Now the electrons and holes have recombined in this region, so we are left with negative immobile ions and positive immobile ions like this, because holes and electrons have already recombined with each other. And you can clearly see, because of this we have layer of negative charges, negative immobile ions on this side, and we have layer of positive immobile ions on this side. So we can say that this is acting as the potential difference. And because of this potential difference, there is an electric field from right to left, that is from positive to negative. There is an electric field like this. Capital E is the electric field from positive to the negative. This is the junction. I forgot to make junction here. This is the junction, and this is the depletion region. Now this depletion region is also called as space charge region, space charge region, or depletion layer. Depletion layer, these are the names for depletion region. Now there is one question: why the width of depletion region? Why the width of depletion region is fixed? Because this hole can combine with this electron. In the same way, all the holes on the P side can combine with the electrons, all the electrons from the N side, and the width of depletion region is equal to the width of the PN junction diode. But this does not happen. What is the reason behind this? As I have already told you, we have electric field developed because of the potential difference, and due to this electric field there is no movement of charge carriers, because this positive layer will repel the holes, right? Because hole is equivalent to positive charge, and this positive layer will repel the holes, so there is no movement of holes, And in the same way, this negative layer will repel the electrons from the n side. So the width of depletion region is fixed, and as you can see, this potential is acting as the barrier to the movement of holes and electrons. It is acting as barrier for the further movement of free charge carriers. We call it barrier potential. We call it barrier potential, or we call it built-in potential. Built-in potential. Right, and we are calling it barrier potential because it is acting as the barrier for the further movement of free charge carriers. Let's talk about minority charge carriers in this scenario. We are done with the majority charge carriers. We have seen there is diffusion current because of the movement of majority charge carriers, and after the formation of depletion region, the majority charge carriers will not combine with each other, and hence there is no movement of majority charge carriers. And as we already know, in case of p-type semiconductor, electrons are the minority charge carriers, and for n-type we have holes as the minority charge carriers. And because of this electric field intensity E, electrons will move to the right and the holes will move to the left. So there is current, and because of drift of electrons towards the positive layer and drift of holes towards the negative layer, we call this current drift current. And this drift current having the direction opposite to the diffusion current. And under steady state condition, the diffusion current is equal to the drift current. Before that, I will complete this. The drift current is due to the minority charge carriers, right? And the diffusion current was because of majority charge carriers. And under steady state diffusion current is equal to the drift current. This is very important point. Diffusion current is equal to the drift current under steady state condition, and we can say that the net current is equal to 0 in case of open circuited PN junction diode. The net current is equal to 0 for open circuited PN junction diode. So this is all for this lecture. In the next lecture, we will find out the expression for VB, that is the barrier potential, and we will also talk about width of depletion region, WD, width of depletion region. So this is all for this lecture. See you in the next one.